Hi, my name is Jada Frisbee. I am a sophomore at UNC right now. I'm an exercise and sports science major and a chemistry minor. And in my free time, I love to watch sporting events, attend sporting events, play sports, exercise, all that fun stuff. So that's what I like to do. And then I really want to be a chemistry mentor because I feel like I was so impacted by their help when I was in general chemistry courses, particularly because they made the large class sizes feel a lot smaller. Oftentimes I was intimidated to ask questions in front of the big group just in lecture, and so I would save my questions and go ask them at their review sessions, and they just really helped to clarify some really foundational concepts that I still use today. And now that I have those concepts down, I would love to be that person that clarifies those concepts for someone else. So this is a titration problem that I chose to work out for this, and it says 30 milliliters of a solution of 0.15 molar NaCN is titrated with a 0.1 molar solution of HCl. What is the pH of the solution after 30 milliliters of HCl have been added? And so the first thing that I would suggest doing is to draw an equilibrium of this, of what is going on in this solution, because I think it's important to look at like an equation type thing rather than a word problem. It just helps you visualize it, and so this is what's going on in solution right now. And the first thing that you need to do numerically is realize that we are adding some volume to this solution. So these molarities are going to kind of change over time because of this addition in volume, so we need to work in moles. So converting to moles is the first just numerical thing that needs to be done, and that's simple, doing converting these milliliter volumes to liters and then multiplying them by the molarities that are given, and that gives you the amount of moles that you are initially starting out with, which is 0.0045 and 0.003. Now that you've gotten here, this is the first portion of your ice initial change in equilibrium box. So the I is what you initially have, which is 0.0045 and 0.003. The C is important because this is when you decide how much you're going to change your solution to get it to equilibrium. And so for this, you have to realize that HCl is a strong acid, which means that it's going to convert as much of this NaCN to HCN as it possibly can, which means you're going to take all of it away, and you're going to subtract what you have of it from your NaCN, and you're going to add what you have of it to your HCN. So with that being said, your equilibrium is going to be 0.0015 moles of NaCN and 0.003 moles of HCN. And that's again because your hydrochloric acid is a strong acid, meaning that it completely dissociates, and it takes as much of this NaCN as it can and converts it to its conjugate acid. So from there, once you do the math, which is pretty simple, we start to look at this Henderson-Hasselbalch equation. And the reason that you should use Henderson-Hasselbalch is because you have somewhat of a conjugate base and you have somewhat of a conjugate acid in this equilibrium. And this is your conjugate base. Here's your conjugate acid. So with that being said, it's simple plug and chug from here. So all you have to do is take your Ka, which is 6.2 times 10 to the negative 10, which was given to you in the problem, and plug it in to find the pKa. And you know how to do that. You just plug it into the negative log of your Ka equation, and then you just add the log of the base to acid ratio. And the base to acid ratio is just 0.0015, which is the amount of moles we figured out was in equilibrium for the base, which is NaCN, and 0.003, which is the amount of moles we found at equilibrium for the conjugate acid. And with that, all you have to do is plug it in your calculator and you get 8.907.